And I'm here to talk about the scope of algebraic effects, which is joint work with Mathieu Pirog, Tom Shrivers, and Maria Skelyoff. So I wanted to start this talk with just a little bit of motivation, and the best motivation I have is ice cream. The way I like to think about effects is that basically that they are like picking flavors of ice cream that you want to be using in a particular context. So computational effects come in all sorts of different flavors. You've got things like non-determinism, you've got state, reader-writer, exceptions, I/O, etc. And one of the things that we struggle with in Haskell, in a sense, is the fact that we're working in a pure setting where maybe it's not so obvious how to integrate things like I/O, etc. But thankfully, we have the power of monads to help us. So, how can we be explicit when we use these particular effects? Well, monads are the way we control effects specifically, so that we can say what kind of effects are ambient at a particular time in the type. But the problem with monads is that they don't compose. That is to say that if you have two monads, F and G, and you put them together, it's not always the case that F and F composed with G is the monad that you think it is, and it's certainly not the case that the monad instance comes free out of the composition. The big question for a while was how can the effects of different monads be combined in a fairly automatic way so that we, the programmers, don't have to worry about rolling new stacks of monads together every single time. And there came sort of two solutions to the problem. One was by Liang, Hudak, and Jones in '95, and the other one was by Plotkin and Power in 2003. Now, most of you will probably have heard of the MTL, the Monad Transformer Library, and that very much belongs in the Monad Transformers style of doing things. But there was another approach to doing this, which was given by effect handlers, which was largely ignored by implementers for a very long time. And roughly speaking, that's what this talk is about. So just as a sort of very high-level overview of comparing these two things, and this is in no way formal, in terms of modularity, they're roughly the same. So you can express compositions of monad transformers in roughly the same way as you can with effect handlers. In terms of flexibility, effect handlers have a little bit more flexibility in the kinds of things that you can do because you can give semantics that can be sort of dynamically allocated at runtime, whereas with monad transformers, you kind of roll your own stack at compile time and you're stuck with the effect stack that you've decided to have. In terms of expressivity, monad transformers can do everything that we'd like them to. But the problem with effect handlers is that there are certain effects that can't be expressed like continuations, so like const t type things. Worse than that, there were some subtle bugs in the way you use effect handlers, which meant that things like catching exceptions wasn't as easy as you might think it would be. But we worked on that problem and resolved it, but we didn't resolve it in a way that I particularly liked until much later in around 2018 when we actually managed to fix it. And that's roughly what the focus of this talk is going to be about. In terms of efficiency, initially there were lots of concerns because monad transformers were very efficient if you did things right, but effect handlers were 10 times slower for just a simple example where you're creating a parser and you're parsing things around using an effect stack. So that was very concerning for a long time. It turns out that the answer to that was to fuse the effects together, and in the end, the efficiency of monad transformers is roughly the same as the efficiency of effect handlers. So that was good too. But this talk is focusing really about the expressivity side of things, and I want to just unpick just a little corner of effect handlers just to make you aware of where they're not quite as good as monads and what we can do about that. Monad transformers, that is. So I'm just going to assume that not everybody here is fully aware of effect handlers, and as a rough guide of how they work, I like to think of them as being like onions. So you have different effects, and you're peeling these effects one after the other, and you're kind of trying to deal with you're trying to make onion soup with your effect handlers. And so you can, and the way you make soup isn't getting an onion, chopping it up, and then putting it in a pan and boiling it and making soup. That's not how you make soup. What you do is to make soup, you start with your onion, you go to the center of your onion, and you make the center of your onion be soup, and then you go to the next layer of the onion, you make that soup as well, and then you keep going out until you've got the soup that's made of your onion. So that's what you do. So the effect handlers approach is really a combination of syntax and semantics, and there's a very clean delineation between the two. So on the syntax side, basically we're going to create syntax trees, and the way we create these syntax trees is by using a functor that shapes the nodes of that tree, and the semantics are going to be given by a fold over that syntax tree. So in terms of what it looks like in code, the syntax is given by the so-called free monad. Now, the free monad you can think of as being a generalized tree where you can shape each node to be how you want it to be. So there are variables var, and that means that you have leaves which contain variables. And then there are node constructors, which I'll call op for operations, shaped by some f, which is a functor, which allows you to decide how many parameters there are at each node and if there's any additional information. So for instance, if f was this OR constructor, OR has 2 k's in it, which means it has 2 continuation points, and so you can build simple binary trees like this with variables as the leaves. On the semantic side of things, an algebra is basically a function of type fa to a for the functor f, and what we're going to do is we're going to evaluate this by having this eval function, which is essentially just a fold. So in the case of a variable, you apply this function gen, which basically is a function of type a to b that takes your variable of type a and produces a final result of type b. And then you've got this algebra, which recursively is applied to the nodes in the right place, which sucks things up. So essentially, you're replacing these dotted nodes, which are the variables, with something in the interpretive domain, which in this case is going to be something like your list. And then you're replacing the OR construct with a plus plus in this example. So it's basically replacing things inside your syntax tree with functions and values. OK. So yeah, I'm just going to use dotted borders to represent variables and hard borders to represent operations. So let's look at some semantics for some simple cases. So one thing that you might do with your syntax tree is have a node that simply says stop, which means I don't want to give you any more values. We're done computing here. So stop k equals stop, which basically means there are no continuation points k on the right-hand side, which means that there's no further code down the line. So that's kind of a terminal object like this. And in terms of giving semantics for this thing, we need to provide an algebra and a generator to the fold function. So the generator is the thing that knows how to transform the variables into something useful. In this case, it's just x, which says that if you're given a variable 3 inside your tree, then that gets turned into just 3 as the result. And in terms of the algebra, well, the only thing that the algebra needs to deal with in this case is the node called stop, and then you just interpret that with nothing. So this is basically failure. OK. Another simple example is void, where this time the syntax, that should say void k, where the syntax has no constructor at all. In other words, you can't construct nodes. You have a tree, it's got leaves, but it doesn't have any nodes. So in this case, your generator, which is a thing that knows how to deal with the leaves, is just the identity function. It takes an x and it produces an x. And your algebra, which knows how to deal with these nodes that don't exist, looks like this. It says case x of, and then there's nothing to do because you can't have a node of this form. So we would use that to actually run code. For something slightly more complex, this is the OR construct that we saw earlier, and you've got 3, 4. And to change what we're doing for once, we're going to use a slightly different semantics, which just says, please pick the leftmost answer. I'm only interested in that one. So the generator is just going to spit out the single value x, so the value 3 gets produced as it is. And then what we're going to do is we're going to just pick out the left-hand branch x's and use that as the result. So in this case, it's like we're replacing these values with just themselves, and we're replacing OR with something like the const function that picks out the leftmost parameter. And of course, you can give the list representation that we had earlier on. And the thing that I just want to point out here is that you can have different semantics for a particular piece of syntax, and that's the flexibility aspect that you get from these effect handlers. OK. Another thing that you can do with effect handlers is that you can actually compose you can compose different effects together, and the way that you do that is by having a co-product of the different effects. In other words, you can combine some f and g things, or f and sig in this case, using a co-product of functors. In other words, you can construct trees which contain OR nodes and stop nodes using 2 different methods. So you can have a tree with OR stop void or with stop OR void, and you're combining these different things, which allows you to have a more complicated structure. OK. So the fact that these trees are different types, well, it turns out not to be a problem in practice, in the sense that you can write down a tree as term and give it a type that's more general than this one and use some type class hackery to make things work out if you want to. That's not too interesting. Or you can do some shuffling around to make sure that the type signature here corresponds to the one that you need when you're interpreting these different trees. And so just to give you an example of what shuffling trees looks like, you've got something called commute, and commute takes a tree of the form f, g, h, and it turns it into g, f, h. In other words, you're commuting the first two terms of that tree. And the way you do that is your generator is simply returning the leaves untouched, and your algebra is saying if you've got some effect, which is the far left thing, then you just shuffle it into the right position by rotating it. If you've got something which is one to the right of that, you can shuffle it again and put it in the effect context. Otherwise, you just leave things untouched. So basically, you can play around with trees and shuffle them around. And the reason I'm showing you this is because I just want to demonstrate that the idea of effect handlers isn't always about computing with effects, standard effects being I/O or state or reader or non-determinism. Sometimes it's also just about playing and manipulating trees at the end of the day. That's still part of it. And you wouldn't normally see this kind of thing happening at the MTL level. OK. Something that we want to be able to do is we want to be able to chain handlers together. That is to say, you want to be able to have a syntax tree with maybe non-determinism and maybe exceptions, and you want to be able to process out all the non-determinism and then process out all of the exceptions in separate stages. And maybe you want to do it in one order, maybe you want to do it in another order. You want to have that flexibility and control. So how do we chain handlers together? Well, roughly the idea is what I just explained. You start with your tree. It's got or and stop in it, so two different kinds of effects. And then maybe you do fail first across the whole tree, replacing all the stop nodes with nothing and the leaves with just something. And then you replace all of the or constructs, the non-determinism, with plus plus and list creation, and then away you go. So you want to be able to compose these handlers in this way. The trouble is that what I gave you earlier on doesn't have the right signature to make this work out, so we need to just massage the types a little bit to make things happen properly. And part of that is going to be made more easy if we have this kind of embedding function, which is something that takes an algebra for f, so that's one effect f, which knows how to, whose carrier is going to be a tree of type G, and augment it so it's an algebra that works on f plus G effects. So you're working with f effects like or, and G effects like stop. And so your algebra, although it only works on or effects, now it works for or and stop effects at the same time. So it's just a way of augmenting your algebra up. And it's a relatively easy function that applies the correct algebra that knows how to deal with f when you encounter an effect x. And in the other case, it just constructs the node that you're looking for. So what we need to do is we need to massage the old version of fail, which is the one on the top, into something new, which is the one on the bottom. And what's changing is the signature. So we need to be generic in the f, which is the other effect that we're not interested in. And so we augment stop to say it's a tree with stop and some other effect f. And by the way, we're not just constructing a maybe a, we're constructing a free f of maybe a. In other words, we're constructing a new tree with maybe effects inside it. So there's this additional, so basically we're doing a tree-to-tree transformation where we're interpreting some of the effects but not all of the effects. Okay, so how do we do this? Well, for the generator, we're just going to basically modify it by having a var constructor outside of the justx, which means that we are creating a new syntax tree. And for the stop, we do something similar. So we can just carry on like that. Okay. In the case of list, it's essentially the same game. We augment the signature with this plus f and free f on the right. We add the var. And then rather than simply taking two values, x's and y's, and appending them together, we now have these x's and y's inside some monadic context. That monadic context is the tree that's beneath you, the tree on the left and the tree on the right. And so what you need to do is you need to say, give me the value that comes out of the tree on the left, give me the value that comes out of the tree on the right, and then I'm going to append them together, and then I'm going to create a variable and put them inside this new tree construct. So it looks something like this. It says, if you've got the value, if you've got a leaf containing 42, then you just make that be a leaf containing list of 42. If you have an OR with two syntax trees with 3 and 4 on the right in the branches, then what the list function does now is it extracts the list from the left, it extracts the list from the right, it appends them together, and it makes you a new syntax tree, which is the appending of these two things together. So it does this. Okay. So why have we gone through all this difficulty? We've gone through all this difficulty so that we can compose effect handlers one way or another way. In other words, so we can do things like write list.fail or fail.list, and that gives you a notion of global versus local exceptions. In other words, you've got non-determinism, and then you can put a stop node somewhere there, and either that stop node destroys the entire computation, or that stop node is just one of many, many possibilities that says this particular sub-branch failed. So if you do a global exception, and you run it on this tree here, where this tree has got a stop node in it, then you'll get nothing because something went wrong somewhere in the system. Otherwise, if you do the local version, which all you did there was change the order in which you do list or fail, what you get out is all of the different answers, but there's a nothing where something went wrong. Okay, so we're happy with this. And effects are everywhere. So you've got exceptions, non-determinism, reader, writer, state, threads, that's all great. And handlers are essentially these functions that know how to operate on the tree, to manipulate the tree from being in one form into being in another form. And so for that, you've got things like catch, every, once, local, flush, exec, run, spawn, fork, etc. And the point is that effects in the algebraic effects setting have to be handled so-called algebraically, which I'll explain in a minute. But handlers might not be algebraic. So the handlers themselves aren't like operations. You can't treat them in the same way, and we'll see why that causes problems later. So we're going to see that in the example of once. Okay. So once is a sort of a prologue construct. It's the one which picks out the leftmost answer in a query, basically. And so we might want to do the same procedure that we did with stop and list, which is to say you massage the type at the top, and then you just make sure that things are monadic enough in the payload, so you have this variable coming up again, and then you just do this mx, being the left-hand monadic computation. And your expectation is that you'll be picking out the left thing, and it should all work out fine. And maybe you expect that when you start with a tree like this, and you do once, that one of them is going to give you maybe a failure because something went wrong, and the other one might give you, let's say, the very first value, or at least that's the intention. So the 4 should be the thing that comes out. But the way we've set things up, you get nothing in both of these computations. Now, it's not surprising when you read the code that that's what you get, but it's not what you want as a Prolog programmer. As a Prolog programmer, you really wanted the 4 to pop out. So it's not as simple as fiddling around with the signatures and making it slightly more monadic. There actually has to be some additional computation to make things work out. So we're a bit sad, but we can fix it. And the fix looks something like this. And it's a bit more complicated than I'd like it to be. But roughly speaking, what you do is this, and this is the interesting line here, is when you spot that there's an OR, you apply once recursively to the left-hand side, and if you discover that there's a stop on that left-hand branch, then you spit out the right-hand branch. Otherwise, you accept the left-hand branch and carry on. So that's the my is the right-hand branch that gets spat out if there was a stop. Otherwise, you do mx. In other words, if there's something that went wrong on the left branch, then you take the right branch, and then you proceed. Okay. But the problem with this approach of doing once is that you're baking in the semantics of once as a handler. In other words, you've chosen what that handler should do, and you're committed to once behaving in this way. Maybe what you have in the Prolog world are these once annotations somewhere in your tree that says, here I want to be able to just collect one computation. But you might think, actually, that's only an efficiency concern. Maybe I actually want all of the results, regardless of whether we have a once there or not. So you want to be able to interpret it sometimes as a once and sometimes as a list, so different interpretations of the same code, which is exactly what handlers are about. And you can't do that here because this is a handler. It's not syntax. So this can be improved. And this is where we get into the idea of scoped operations. And a scoped operation is something which you would normally treat as a handler, but instead you want it to become a piece of syntax and operation so that you can interpret it in different ways later on. So once would look something like this. It's just a single node in your tree that says, I want to do the computations underneath just once. And it may seem that it's good, but this approach is also broken. And to understand why, I need to tell you a little bit about algebraicity and why people call them algebraic effect handlers and not just effect handlers. So algebraicity is easy to see with the OR construct. The OR construct is the one with 2 continuations, And here's a tree with OR 1 and 5. And if you bind that with the function that just splits the node up and does x plus 1, what you end up with is a tree that looks like that on the right, where one way to understand what bind does is it's variable substitution. It takes the tree on the left-hand side, and for each leaf, it applies the function on the right and grafts the result onto the part of the tree. So here you've got this 1, you make x be 1, and then you graft on the result of substituting that x in place. That's the left-hand branch. And then you do the same thing with the 5. You take the x, you substitute in 5 for x, and then you get the right-hand branch, and then you're happy. So this is demonstrating the algebraicity of the OR function. And more formally, it looks like this. It says that if you have OR P1, P2, and you bind, I wish this was a bit taller. Can I lift the, no, anyway. So if you have OR P1, P2 bind K, then that should be the same as OR P1 bind K, P2 bind K. In other words, the K gets distributed right into the parameters of the operation itself. So let's think about how once should behave. So once is this thing that should pick out the leftmost argument. That's the number 1. So the result of this computation on the left should be just the one node and nothing else. And so 1 bind this function shouldn't be this thing on the right-hand side, because we don't want to get the results 1 as the result of this thing on the right-hand side. We really want 1 and 2 in some sense. So in other words, what you want is you don't want this thing. You want it so that once OR 1, 2 bind that is this structure here on the right. Now, the difference is that once you've picked the 1 here, you're committed to this branch being the one that you want. And then you have to bind to simply the 1. And so the result really ought to be just this box here, rather than the whole thing, rather than just the number 1 itself. So in other words, the once should be kind of a local computation rather than a global computation. You want to be able to pick out the answer and then bind, rather than look at all the answers and bind out just the very first of all of those. So our goal is to treat once like an operation, and the trouble has been that the bind has been able to interfere or go into too many parameters at once. It's been able to walk into all the different options. So the solution to fixing this is basically you have a once operation, which we say is some kind of monadic computation E, whose payload is of type A, but underneath that once is the tree that you want to just have happen the single time. And notice that here I'm using this x parameter rather than the a parameter, and that's going to be existentially quantified so that you don't get access to the parameters or the tree inside the once, unless you escape it through this continuation k, which knows how to convert a single value out of that tree into the final computation that you're looking for. So categorically, this thing turns out to be an interesting data structure, but the thing that I want to point out is that it's quite close to the presentation of the free monad. So you've got variables, so this is where the leaves come from your tree, and then you've got some kind of signature, which corresponds to other operations, and that's going to be the ors and the fails. But you additionally have this strange gamma operation, which says that once is a special operation with an existential that hides away the fact that it's got a tree inside it whose variables you can't touch. So that's what happens there. So you've got basically a kind of a tree structure underneath the gamma. So you've got this gamma EX, which says it's an ordinary tree except that the variables are of this hidden type X. And then you have this continuation parameter, which basically says for each of those X's, I know how to escape and make you a tree of type A all over again. And you combine these two things out, and then you get a piece of syntax all over. So that's the equation that we were working with, but it's not terribly useful as a piece of code. And so the task or the challenge was to try and work out how this translates into something that we can actually implement. And so this can be reduced to this other expression through some diagonalization argument, which in turn is some pretty simple Haskell code. So it basically says you've got some variables of type A, or you've got some signature sigma, where sigma's been replaced with this f of ordinary functorial syntax, or you've got this gamma with this sort of syntax inside syntax, or tree inside tree. So you've kind of got a context that's slightly higher, that is higher order. And that's what I call a scoped construct. And this is where you've got a kind of a subcomputation where the intermediate state can't be observed from the outside. So that all kind of works out nicely, except that there's one serious problem with this particular approach, which is that the algebras that you write are far too powerful. So the algebras over this data type give you access to the entire subcomputation, the entire structure of the tree. And the thing that I like about algebraic effect handlers is that you should be able to fold through the entire data structure step by step, just like you fold through a list. And what this algebra allows you to do is sort of wholesale look at the syntax, investigate it in any way you like, and then give you the answer, when in fact what you want to do is, again, have a fold through even the intermediate trees as well. So this isn't quite what you want. And to fix that, we had to go through this process of creating these indexed carriers. So the idea is roughly that if you consider this tree example, we're going to, rather than having a once node up here which has this strange type, we're going to annotate a tree with these brackets, so left and right triangles, that say this is where the scope of the computation is, or this is the scope of the things underneath me. The way that you would compute this tree is you start with the thing on the left-hand side, you apply the ordinary algebra A starting from the bottom. So here you're going to interpret these ORs and append lists together. And then you need to do something with these triangles. And that's what we call promotion. So promotion takes the leaves, somehow promotes them into some kind of computational context that has more information about how to deal with the complicated scoping. In this case, we're going to go into lists of lists. And then we carry on applying the ordinary algebras A to get to this context here where you can just append things together. And then you have to come out of the bracket, come out of the once, and so you demote your computation. In other words, you go back to the ordinary world where you're allowed to continue computing in the ordinary way. So that's kind of the rough lines of what goes on. And for the eagle-eyed among you, you might notice that something's fishy going on here because the types are changing of these leaves halfway through the computation. You've got ordinary lists here. Here you've got lists of lists, and you go back to lists again. So something is happening at the type level, which isn't what we would normally expect when you're just doing tree transformations. And what's happening is that each tree level is actually indexed by some kind of natural number that tells you something about how the context is changing and gives you a new data type that's relevant to that kind of context. So this is kind of where you end up going, and it's still Haskell 98 in Chonga's sense of 98 extensions, but it works. So the idea is that you have these natural numbers n flying around, and you have these algebras which are parameterized over natural numbers, and then they kind of fit in. And so your algebra A, which is the ordinary algebra that we were presenting at the beginning of this talk, simply passes through of type f an to an, so the n's aren't being messed about with in that case. But promote and demote, they go up and down, so one adds to the output and one adds to the input. So that's how you get away with having this P and D having different types, and while your tree changes types as it goes along, and that's where you specify exactly the behavior of those things. Okay, and you can tell that things are getting more theoretical because the font has changed. So, basically, we started off with these kind of algebras, and they could be packed up like so. And what remains to think about is how do you actually fold through the data structure itself. So the first two lines are exactly the eval function that we had for the free monad earlier on, and it's only this last line that's interesting and also hard to get your head around. So what you're doing is you're saying something along the lines of, we're going to fold the inner context, we're going to apply the ordinary algebra, but we're going to sort of F-map this one level in, and then we're going to fold the whole thing up. So this part of the code in here is dealing with the inner computation after it's been appropriately promoted. In other words, this is dealing with the subtree. And then you finish dealing with the current node, and then you demote the whole thing. So that's what goes on with scoped operations. I wish I had a better explanation. I'll work on it. So, in practice, all you have to do if you want to implement once is write this code, right? What could be easier? This all gets a little bit crazy because the carriers that we're dealing with are nested carriers where at each level, you're adding one layer of complexity. So here you have, at level 0, it's just the carrier A, which contains the payload that you're interested in. But for each successive level, n, you're going to recursively add lists of things. So at level 1, you've got a list. At level 2, you've got a list of lists. At level 3, a list of lists of lists, and so on. And then the interesting part here is going to be, what do you do when you demote and you promote? Well, when you promote, you pull out the list that you have, and when you demote, you add an extra layer of listiness around the whole thing. And that's going back to this intuition that we had in that initial diagram, where at some point, you're adding a level of lists, and at some point, you're removing a level of lists, and this is where you write this code. OK. I've kind of pointed out that what's going on under the hood is a bit complicated, and it is complicated. So I wanted to just give you a glimpse of that before terminating. So what's really happening is that we have these so-called indexed carriers. So we're working in a category not C, which is the usual Haskell category where types are the objects. We're working in the category C to the N, where types are now not the objects. What are the objects are indexed types. So where you provide an index that tells you what's going on in this particular position. And we need ways of moving between these different levels, and that's what these left and right triangles are, which were precisely the ones that we had earlier on, which told you to promote and demote from one context to another. And what's going on here is that you're just saying something about we're going one level of nesting in, or we're coming back a level of nesting out. And in this setting, you can lift ordinary functors easily enough by doing it pointwise at each level or at each index. And then you need a way of being able to drop from computations in this crazy index world to the ordinary world, and a way of going from ordinary computations to index computations. And so the way that we drop down is we say, well, we've got a category of index things where you've got computations going on at all natural numbers, but level 0, that's the level where you get the final answer, is the only one that matters when you're actually doing final computations. That's what this corresponds to. And then on the other side, you need a way of being able to say, I've got a computation that exists in Haskell. How do I promote it so that it exists at all levels? And, well, what you do is you say, initially it's in Haskell, so it's just at level 0. And every other level, well, we don't quite know what the type is of that thing, so it's going to be void. So the theory dictates that there's this really cool structure. There's an adjunction hiding around in this whole thing, which allows basically the free monad to be constructed in the right category. I don't really want to go into the details of that other than to say it's very pretty. And then the proofs of this stuff all working out and the proofs that the algebras are the right ones that you're looking for are complete nonsense unless you spend lots of time looking at them. So I'm not going to go into that either. So basically, to conclude, I wanted to just highlight something about the difference between effect handlers and MTL. And really, the takeaway message here is that while MTL handles things like local very beautifully, it's not such an easy thing to do in the effect handlers world. So when people sell you that effect handlers are better at everything, well, that's not strictly speaking true. They can do lots of things that monad transformers can do, but there's a lot of work going on behind the scenes to make that actually happen. So there are some scoped effect libraries that use some of these ideas in a much more pragmatic or understandable way than what I presented here. So Fused Effects by Rob Ricks and Patrick Thompson goes into some of this, and so does Polysemy by Sandy McGuire. And I think you should try them out. So they are much more approachable than the theory would dictate. And I think that these guys have worked extremely hard to make this stuff usable by mere mortals. And so I can recommend that you go and have a look at the work they've been doing, because it is really wonderful. I also wanted to just take this as an opportunity to say, join us. There's a great team of us working at Imperial. So Matthew Pickering is at Bristol, but he's a temporary RA at Imperial at the moment. Chunga and Jamie are my PhD students. And I'm still looking for research assistants and postdocs. And so if you'd like to join the team, please apply. So there are adverts out at the moment. I'd love to talk to you. With that, I'll conclude, if you have any questions.
I didn't understand all of what you said.
Sorry.
I was just wondering, what exactly were you indexing with the natural number? Was that like the position in the list of composed functors that free represents?
Yep. So maybe the easiest thing to do is to show you the picture. let's go here. So what you're indexing is, roughly speaking, how nested you are under a once. So you could have a once construct, which nests you once. If you have a once inside a once, you're nested twice. If you have a once inside a once inside a once, you're nested 3 times, and so on. So it's basically telling you how much ambient context there is, how far deeply down inside the structure you are of this weird once construct. So, in an OR, if you have like a tree full of ORs, you don't usually count how many far down the ORs you are. It doesn't really matter. But with the once construct, it does matter how far down you are. And another example of this is in state. If you have like a local state, and then inside that local state, you've got another small local state, and inside that, you've got another one, then it's just like watching the movie Inception, right? And so you need to have a kick, which allows you to come out of one level, and that's what the demote is doing. And you need to be able to sleep to go into another level, and so that's what the promote is doing. That's roughly what they correspond to.
Thank you.
Okay. Oh, I think they want to give you a
Sorry,
microphone.
just wait for my... I'm not that fast.
So the scoped operations like once, do they go in the signature G? So G is another signature, right?
Yeah, exactly. So the way this works out is F is what I called sigma in the theory part, is going to be ordinary operations which don't need any special treatment. And G or gamma is going to be the strange operations for which you do need to keep track of the indexing, or you do need to keep track of the nested context or scope. Yeah.
Thank you. It was a cool talk. I was wondering, is this talk based on a particular paper about this, or is it kind of an aggregate thing of a lot of things, or can we read about this somewhere?
Yeah, so the single paper that this encapsulates the most is one called Syntax and Semantics for Handlers with Scope, which is by Maciej Pirog, myself, Tom Shrivers, and Maria Skelioff. But I can give you a link later as well.
So if I understand it correctly, the promote and the demo are either, one of them is doing the semantics and the other one is cleaning up or setting up, right?
Yes.
So what is the advantage of doing that as opposed to just having 2 operations in the language, one that does the setting up and one that does the cleaning up? Or because local could be done in terms of put and get.
Oh, I see. So promote and demo are useful in the same way that algebras are useful. So you can write a recursive function that deals with with a syntax tree and does everything you need it to. But algebras are useful because they give you a very structured way of dealing with your computation. They forbid you from doing naughty things. They make sure that you're doing things layer by layer in a highly structured way. And in the same way, you could have arbitrary functions that do the setup and the teardown, but you maybe have too much freedom there, and you can introduce bugs. Promote and demote keep you on the straight and narrow so that you can only affect things one level down for the current level, and you can only go one step up the other way. So it limits your power.
Any more questions? Nicolas? Okay, thank you once again, Nick.
Thanks.
We'll take a slightly extended break.